Okay, folks, we're going to be looking at map projections this week, which are kind of easy to grasp, at least the main parts of it, but they're also incredibly important to understand in terms of why we're doing what we're doing and how the maps we make, what they might actually be able to do or not be able to do. So this is important stuff, and unfortunately not a lot of people talk about it when you're first learning how to make these maps and work with GIS and all that. So this will be an important and very practical introduction here. And so what I'm going to do is I'll talk about the concepts of map projections, and then there'll be another video that's an exercise. We're going to download some data, practice that again, and we'll get into changing the projection / coordinate system and get into why we would want to do that. So the idea is we take something like the Earth, reality, right? The actual planet Earth, and it's very easy to shrink it down and represent it as a globe, right? As a smaller version of the bigger real thing. The problem, though, if we're looking at the globe representation or the actual Earth itself, is that this round, technically round-ish, it's a geoid, not a perfect sphere, but a round-ish planet, it's hard to see the entire thing at any given time. In fact, looking at it right here, we're actually seeing less than half of the planet. We have a pretty good view of South America and Central America, parts of North America, but because of the fact that it is this round thing, we can't see what's happening on the other side, and we even have a hard time seeing what's happening as the Earth curves around the sides here. So what we often like to do is look at a flat map. And the amazing thing with a map like this, and something that is truly amazing from a geometrical point of view, but also something we don't tend to think of as being truly amazing, is the fact that we can see the entire world at one time, and we can see it orthographically, which is a fancy way of saying we can look straight down at the Earth. So our eyes, the gaze of our eyes, hit the Earth's surface at a perfect 90-degree perpendicular angle, and that takes place everywhere on the planet at the exact same time. That is impossible to do in reality, but maps allow us to do this. Okay? But we're going to get into what that means, because it's not as simple as just unrolling a globe and voila, you have a map. There's more to it than that. And that's what I'm going to be covering here. Now, maps themselves, it might be good to define them. And the best way, I think, to define them is that they're scaled representations of reality. Okay? Scale, talked about a little bit last week in terms of data, and we'll talk more about this stuff as we go on. But what scale is, and again, the main idea is that it's a ratio between how big something is in reality compared to how big it is on the map itself. All right, so that's the scale component. It's a representation as well. I think it's always important to remember that a map is not reality. It's a representation. It's something that a cartographer chose to create. He or she made certain decisions to add this thing, leave this thing out, use this color, use this concept, whatever. But a map is not reality. We want to keep that in mind. And so we take these maps, we make them out of points and lines and polygons. These are the feature classes we've worked with. We also have type, so the labels we put on there. All right, and so that's, again, like this image we've seen before. This is a perfect example of this is a representation. And we can look at the greater Los Angeles and kind of Southern California area that's highlighted here it's a representation that's pretty good. We get a sense of what we're looking at. Maybe we're familiar with these areas. But it's also, if you are familiar with something like downtown Los Angeles or Long Beach or Malibu or whatever, you miss some of the details, some of the actual what it's like to be in this place. So that's part of the whole representation thing, and just something to think about. Now, before we get into actual projections themselves, it's worth talking about the basic shape of the Earth. And we have a couple of ways to map these things. We have here the sphere and spheroid. And so a sphere refers to a perfect 360-degree sphere. It's a perfect ball, right? A spheroid, it's also sometimes called an ellipsoid in this mapping speak, but it's like a squished ball, kind of more like an egg rather than a perfect sphere. Okay? And so we can map out the Earth, and I'm not going to get into all the details in terms of geodesy, but we know the Earth is not a perfect sphere, and we used to believe, thanks to Newton, and it's still true to a certain extent, that the Earth is not only not a perfect sphere, but it's kind of this squished sphere, this squished ball that we have. And it has to do with a centrifugal force, excuse me, at the equator. It's the rotation of the Earth that causes the equator to kind of bulge outward. So this example that we see right here, this equatorial plane, this is larger right here, this distance or this semi-major axis versus the semi-minor axis. We have this, the semi-major is longer, and semi, just think of it as radius. It's half of the diameter. So the semi-major axis is a little bit longer, semi-minor a little bit shorter. This Clark 1866 is a specific model of the shape of the Earth that we use in a lot of older maps in North America, stuff before 1980. So you'll see this Clark 1866 from time to time referenced, and this is simply a way to model the shape of the Earth so that we can have this good starting point, this good concept of what the Earth actually looks like. Okay? Now we've since, this Clark 1866, and like I said, it's pre-1980 maps, we've since further refined our model of the Earth. We know that the Earth is a geoid, and geoid is simply a fancy word that says it means Earth-shaped, right? We say the Earth is Earth-shaped, and that's because we can't actually fit the Earth into an already existing shape. It's kind of this funky thing. Not a perfect sphere, but it's also not a perfect spheroid or ellipsoid. So the geoid, it's a complex balance of gravitational pull and mean sea level and different things like that. All you need to know is that it's the better representation of the shape of the Earth. And so we use this GRS, or Geodetic Reference System of 1980. That's a newer model that we have. And it's got that same idea of a semi-major and semi-minor axis. They're just different dimensions. And this image over here is showing some of the different models and how they're laid out and where they're placed. And we'll talk about WGS 84 in a bit as well. Okay, but with just a few different ways to model the Earth. It's a few different ways of figuring out where the center of the Earth is, kind of where we start some of our maps from and all of that. You don't need to worry about these numbers here, but it is good to at least have a sense of these models and what they are. To know things like that GRS 80 is going to be more accurate, more true to the shape of the Earth than that Clark 1866. Now, another thing we have here is what's known as the horizontal datum. So we're going to be getting into coordinate systems, which we haven't really talked about yet, but it's this idea of things like latitude and longitude. right? Some grid system that we overlay over a globe or a map or whatever. And so we have this good reference grid so we can figure out where we are, where we want to go. We can take measurements, things like that, right? But we have multiple coordinate systems, and we also have multiple horizontal datums that tell us where our coordinate system is actually starting, all right? The ones that we'll primarily see are first, there's the North American Datum, or NAD, 1927. So this is an older one. It's based off of that Clark 1866 model, that spheroidal model of the Earth. It originates in Kansas. That's kind of the origin point there. And then we've since replaced that in this country for a lot of the stuff we do with NAD 1983. So the North American Datum 1983, which uses that GRS 1980 geoidal model. And it's gone for this more three-dimensional thing. It uses the Earth's mass itself was important because of the gravitational pull and how that influences the geoidal shape and all that stuff. So really, the thing to know here is that NAD 1983 and that GRS 1980 system, it's a better, more accurate system. It's why we made the effort to switch over. But when you're working with maps, depending on when these things were actually made, you might work with a lot of stuff that was originally in that 1927 system. And then another thing that we'll see throughout this course, and you'll continue to work with, is the WGS 1984, the World Geodetic System of 1984, which is both this model of the Earth as well as a coordinate system. And this was a way to ensure that we weren't primarily focused on North America. So like that NAD 83 and GRS 1980, that's great for mapping within the United States. But as the globe effectively got smaller, as we started doing more international work with things like GPS and all of that, just navigation in general, as this got more advanced, as we started relying on a lot of this stuff around the world, we worked toward this global system. So GPS in general is based in WGS 1984, kind of defaults to that. But then there are a lot of the maps that we use might be based in NAD 1983. And so that's another thing we'll see kind of later on. But we want to be aware of the data we're using. What was it actually made in? Because if you give me, say, some latitude and longitude coordinates, and you give me a whole list of these things, but you don't tell me what datum you used, I can plot them, sure, but they might be in a totally wrong place. They could be off by hundreds of feet, all because you were working in WGS 1984, I was working in NAD 27, and it just, these things don't necessarily talk to each other, right? So just because your phone, say, tells you a specific latitude and longitude coordinate, it doesn't necessarily mean that you can then go to a map, plot those coordinates, and know exactly where you are. There's more to it, and so we'll see that a little bit, and we'll get into that. Okay, but that's the coordinate system and datum idea. But what we'll also see is that ArcGIS kind of blends together this horizontal datum, these models, and this concept of a map projection. So it gets a little overly simplified with how ArcGIS uses it, but now I want to take some time and talk about this this idea of a map projection. And it really comes down to the idea that we have our round geoidal Earth. It's a round thing, and we want to put that shape onto a flat piece of paper. And it turns out you can't take a sphere or something sphere-like and make it lie down flat and perfectly so. Right? The great analogy we always use is you take an orange. You can peel an orange in a variety of ways, but you can see with these examples here, like trying to make the thing lie flat, it's going to look funky, right? It's not going to look like a map we're used to. We wind up destroying the surface of the orange in order to get it to lay down flat, right? So we can't just peel a globe, right? This is what we would be left with. And we never see maps like this because this is a terrible map. It's hard to look at. It's rough. If you want to say, look in North America here, we've torn it up into all these different sections. It's kind of hard to measure from here to over here or to get a sense of the spatial relationship between things because of these gaps in here. Same thing with like Antarctica is just destroyed. Asia, same kind of deal. All right, so that's not useful. So the question is, what can we do? How can we get to this? And the solution is a map projection. Okay, that's the idea. That's what we're looking at here. That is, the globe has been projected into this map form. Okay, so a map projection is this systematic way to take the globe, which is just a shrunken down version of the Earth, and it's a systematic way to reproduce that. And this term graticule refers to something like latitude and longitude, and it's how we can reproduce it on a flat surface. Okay? But the trick is, with this, whenever we do this, we're going to introduce distortion. Okay? And distortion means there's some kind of stretching, tearing, pulling, tweaking, however you want to describe it. We alter the Earth's surface in order to make it look seamless and nice. Okay? That's where there's no way around it. Okay? Now we can project the map in different ways. We've got some different examples here. We'll get into some of these terms like conformal or conformality, equivalence, equidistant. These are different ways to project the actual surface. So we're looking at the continent of Africa. It's a little different looking at it. Might not be totally obvious, but there are different ways that we can make it look. And really what that means is we've introduced distortion into some different areas. Okay, that's the idea there. And this is an image from Arthur Robinson. It's a classic cartographer in the kind of after World War II, really advanced American cartography and just cartography in general. An important figure, and this was in his classic textbook. He had this blue bald man that he used and drew it onto the Mollweide projection, which is at the top, and then reprojected it like the Mercator in the middle here. And so you can see the head kind of swells up and the neck and so on. So kind of showing how, not saying that this top one was perfect, but just saying how we go from one projection to another. It really highlights how the same things get distorted. Okay, what's going on with this distortion? All right, now we have many, many ways in which we can do it. Here, someone else has taken this idea of the bald blue man and drawn his head repeatedly on some of these different projections. So we have hundreds, if not maybe thousands of projections from which we can choose, but not a single one is perfect. They all have distortion in some way. Okay, so that's important to understand. But if we know where that distortion is, we can select the right projection to ensure that our map is going to work for what we want it to work for. Okay, and we'll get examples of that. So we want to know, for example, the Mercator projection. We'll get into that. We want to know when that would be useful, right? Or the sinusoidal or the Winkled triple or whatever. Any of these different projections we have, we want to know why we would want to choose one so that if we're making a specific map, we can make the best possible map for the intended use. And so that's what I'm trying to introduce here. So with this whole map projection idea, I'm going to quickly get through some of this stuff because it really doesn't matter that much as you're starting out. You're not going to be making your own projections, but it's good to know effectively how this stuff works. All right, so when we're making a projected map or coming up with this map projection, there are a few decisions that have to be made, like what kind of map surface or projection surface will be used, the orientation of that surface, the light source itself. And so all of this is going to determine what properties your map is going to retain. What is it going to keep from the globe, of this representation of the larger Earth? What qualities can we keep with the globe, right? Where can we not have distortion? And therefore, where does that distortion then have to show up? So like I said, let's kind of quickly get through some of this here. Now, these surfaces simply refer to the sheet of paper, if you want to think of it that way. And this goes back to classic, ye old times when we first started doing this. The idea of a map projection was that we were taking light and projecting the shapes from a globe onto a sheet of paper. Okay? And so it was a real kind of low-tech concept. It's different today, but we still use a lot of these terms. And so we have really 3 sheets of paper that we could use. And there are some exceptions today, but we're going to stick with this. We have planar, or also azimuthal, conical, and cylindrical. These planar projections are very straightforward. We just take a flat sheet of paper and we put it somewhere on the globe itself. So this example is showing if we want a map of the North Pole, using this type of surface is very useful because we get a great idea of what's happening at the Arctic, say. Now it's going to get worse. Distortion is going to increase as we get further away. You can kind of imagine a light being shined up through the globe and projecting that, and the shadows that would be projected would get more and more distorted as you got further from the surface of the globe itself and onto the projection surface. So it's a very simple idea, and it's great for, say, a map of the Arctic, but if I want to show, say, Southern California, not going to be the greatest choice here. Okay, conical projections, it's a cone. So it's the idea that we take a cone and we slap it down on one side of the globe here. We project that, and then we develop it, which is a fancy way of saying we cut it and unroll it. And so this is great for maps of, say, North America, where we've captured that. If we don't need to see South America, we don't need to see Asia or Africa or anything else, this is a good way to do that. And standard line here refers to orientation. We'll come back to that. So there's the cone thing, the conical, cylindrical, same idea. It's a cylinder we put on there, project it, develop it. That's what we get. And then orientation is where we're actually placing these things. Okay, so it's the point or line of tangency, or what we call a standard line, is where that projection surface is actually touching the globe. Okay, and this is important because that line of tangency, or that standard line, is the place where there is no distortion. It's true to reality in terms of shape and size and where everything is, what distance it is, that kind of stuff. Okay, so here's an example. Looking at orientation, these would be 3 cylindrical surfaces. This normal one here is where that standard line is at the equator. Transverse is where we flip it, so it's effectively the standard line is connecting the North Pole to the South Pole, and then oblique is anything kind of in between there, right? And so this is important. If I need to have a map that's really highlighting, say, the equator, right? I'm looking at the Congo, and I need to have a good sense of what's happening there. I'd want something like this normal orientation, right? But, maybe I don't need to know what's going on at the equator. It's more important to kind of follow a line of longitude here. Transverse would be useful. And so this is why it's important. You need to know what it is you're actually making this map for. What's your area of study? What's the most important place? And that'll help you decide, okay, what kind of surface do I need? What kind of orientation? And so on. All right, and so here again is showing that idea. You can see these standard lines. So it's standard line or line of tangency. It's where these things are touching. That's going to be the truest section of that map, right? So whether it's at the equator, or in this case, at this planar surface, it would be at the North Pole itself. Those are the areas that are not going to have distortion. Okay, we can also have what's known as a secant projection, which is where the surface, we actually put it through the globe. So you can see we get two standard lines, and therefore it helps to increase our accuracy, right? So you may see something that's a secant projection. That's a useful thing to have. Again, say a map of North America. That's great if we can have two places where there is no distortion. It helps make the U.S. incredibly accurate, so it's good for a map of, say, our country. And then finally here, the light source. You can see with this image, it's showing this concept, and where we put that, in this case, light bulb, as a candle to start with, but where we're setting that will change the shadows and change some of the properties that this map retains. All right, and I don't think I have, antipodes on the opposite side. We can put it in the center. We can move this thing around, but don't worry about that because we're not going to play with light bulbs in here. And then so again, with these three choices that we have, what surface are we going to use? Where's that line of tangency going to be, and so on? That will determine what this projected map is good for. Right? We're always going to have distortion, but we're going to have different types of distortion. So no matter what, some of this distortion will occur. But if we know which of these properties your map will maintain, then we could be okay. All right, so I'll get into a few of these: conformality, equivalence, and then distance and direction. These are the four things we should be aware of. So conformality is shape. All right, it's where we take the angles that are on the globe and we're able to transfer them onto a flat surface. Okay, so if we have proper angles, it means that we have proper shapes, right? Think, a square is, four lines, and the angles are all 90 degrees and all that. So if we can maintain these angles and how these different lines meet, we're going to maintain proper shapes. And a clue that you're dealing with a conformal projection is that the latitude and longitude lines will cross at right angles. And now one issue is that scale is the same no matter where you are on the globe. So if I'm measuring something, say down here near us, or around Los Angeles here, I can measure to the north, I can measure to the south over a short distance. Scale is going to be the same. But if I'm traveling from here, say further north, that scale is going to change. And this isn't a true scale here. It's two images that I just put together so it would make sense, hopefully. But we kind of have this hourglass look to or would if we had a scale bar right here. And so this is something to think about. If you're making a map of the world and you're using this Mercator projection in ArcGIS, you can insert a scale bar like we've already seen earlier. You can do that. It's not necessarily going to be correct, right? It should be based, I believe what it's going to do is use the scale at the equator, and that's what we're going to get. But it can't actually produce something that looks like this that shows that change in scale. All right, so we need to be aware of that. We need to be careful of that. If we're actually trying to make a map that would be used for navigation, say, over large areas, which is something this Mercator projection can be good for, well, we need to be cautious that these automatic things that ArcGIS does, and they can be very useful, might not be useful in this situation. All right, and so as I said, this idea of the Mercator projection here, it's a conformal map projection. It's one of the oldest ones that we still mess around with, and that's because it was the first one that really allowed somebody to draw a line from point A to point B, draw a straight line, and it would maintain proper direction. So if, say, that line you drew was in a northwesterly direction, you could point your ship to the northwest and you'd eventually get to your destination. Right? No other map could do that up until this point. up until Mercator himself came up with this stuff. Okay, now the problem, though, is that we do have this distortion, and it's a distortion in terms of size, which I'll show you. And then it's also not the shortest distance between these 2 points. So yeah, I can go northwest, I can get there, but there might actually be a shorter way to get there that's not apparent based on the map itself. So size. Here I took a composite satellite image of the world, and I projected it using the Mercator projection. And typically, we don't see something that looks like this because it's clear that Antarctica is a mess, so we crop it, right? We see something that looks like this. You just see a little bit of Antarctica kind of peeking up from the bottom here. But this is Mercator's projection, right? And you can see the latitude and longitude lines, which I have in here for reference, that they're crossing at right angles. But the problem here is that size is screwed up. So while we can maintain shape, things are great in terms of shape, sizes are pretty rough. Okay? And so this is an issue when you're comparing areas around the world. One classic issue is back during the Cold War. We've got the United States there and what was the Soviet Union. And the Soviet Union looked gigantic compared to the United States. Right? Alaska looks pretty big. It's actually too big in reference here. But this, this was something that Americans didn't quite like. In fact, I think this is why Robinson is known for his Robinson projection. It was a way to show sizes a little better. And I think part of that, one of the reasons why he was tasked with this thing was simply because of Cold War propaganda. It was kind of imposing to see the Soviets looming over us. Okay, but if we go back to the actual globe itself, you can see on the left here, Alaska gets a little smaller, and the Soviet Union also gets smaller. And that's because these sizes up higher and closer to the pole are they're distorted, they're expanded, and we'll see more examples of that. Here's another thing I did where I took a yellow circle and I just copy and pasted it all over the globe and then projected it to that Mercator projection. And you can see these yellow circles in reality, if you want to think about the globe as being reality, are the same size, but here you can see that distortion that takes place, how places get bigger, sizes get bigger. And then also the idea of not being the shortest distance. We have an example here, Kansas City to Moscow. If you draw that line, it's perfect in terms of direction, but distance is screwed up. Okay? This great circle arc, this route from here flying up through Greenland and down, that's actually, if you look at a globe, that's actually the shortest distance. But Mercator's projection couldn't show that. Again, it's because of that size distortion. Okay, now equivalence is the other major property, and equivalence means size. Okay, these are equal area projections. Sizes are maintained. So stuff is the proper size, but it means that angles are screwed up. So you can either have good shapes, good angles, or good sizes. Okay, so when we look at latitude and longitude, or parallels and meridians, they're not going to consistently cross at these 90-degree angles. Okay, so size is great, but shape is off. We can see this example in the image right here. These are all the same area, so they're all the same size, but they're just 6 different shapes. Okay, same thing if we're looking at countries. These Perus, these 3 Perus are all the same size. They're just different shapes, right? And so the question could be, well, why would we want this? This is very useful if we don't really care about the shape of things, but we want to measure, across the globe, the size of things. Like picture remaining rainforest. I can measure how much rainforest we have in terms of square miles or acres or hectares or whatever unit I want, I can measure that on either of these three maps, and I'm going to get the same answer. And then the good news is I can measure the Amazon rainforest all over South America. I can measure the remaining rainforest in the Congo. I can go to Southeast Asia. I can go all around my map, measure this stuff, and the size is going to be consistently the same. I don't need to worry about that distortion as you get further from the standard line or something along those lines. And a clue, too, that you're working with an equivalent map projection, something where sizes are the same, is that Greenland and Mexico, in reality, are roughly the same size. It's not perfect, but they're close, right? So if you're looking at a map projection, you can look at Greenland, you can look down at Mexico, and if they look close, then you're dealing with a map projection that is equivalent. It's maintaining equal area. So this is a sinusoidal projection, and so you can see Greenland up here, Mexico down here, the latitude and longitude lines, they meet at 90-degree angles here and here, but we get out here and we can see that we get some obtuse and acute angles off to the margins, right? So shapes are screwed up, but size is good. So if I'm measuring the size of something, this would be an excellent map. And I go back to those yellow circles, they get stretched and tweaked, but generally speaking, that size is much better maintained than compared to the Mercator projection that we saw. This is a good interrupted is the term we use. I think that's the term that ArcGIS uses as well. And this is kind of cheating because it is kind of like peeling that orange, but done in a way that it's a pretty good equal area map. And as long as you're not mapping something like Antarctica or Greenland or the oceans themselves, this actually works pretty well. And again, you can see those circles and how they work. Okay, now direction and distance are the two minor properties. We won't dwell too much on here, but direction just means direction is true. And we can also call these azimuthal projections, in that if I draw a line at a 45-degree angle or a 260-degree angle on my map, that's also going to be the same thing that exists out in reality, right? So we can see that with the Mercator projection. There are also others, like we have these mnemonic projections where that direction is in fact true, okay? And so if I need just the direction from, say, the South Pole to other places, that's useful. Of course, you can see with this one, size is horribly distorted. So again, it's this issue of compromise and thinking about what you need to actually do. And equidistant map is where we're maintaining proper distances or great circle distances, which is not something we need to worry about. It has to do with chopping the Earth into two equal halves. It's technically the shortest distance between 2 points on the globe. But that's what an equidistant map is going to show. It's going to maintain that proper distance, right? So this is the azimuthal equidistant projection. So it maintains direction, maintains distance within some degree of certainty there. And so that's what these are used for. They look pretty funky, but they can be useful if you know what it is they're used for. And then finally, we can also utilize what's called a compromise projection. And these are projections that don't maintain equivalence, don't maintain proper conformity. They kind of meet in the middle. They compromise. So there's distortion all around, but there's enough distortion here and distortion there where the map just looks good. And this is fine. Let's say I'm not going to use this map for measuring remaining rainforest. I'm not going to use it to sail across the Atlantic Ocean. It's simply a nice reference map for what's happening around the world. That's where a compromise projection comes in handy. And this is the Winkle triple projection. It's what National Geographic likes to use. It's an attractive projection. It looks cool. It minimizes distortion. Greenland is a little bigger than Mexico, but not in the same way that, say, the Mercator projection is, right? The angles at which the latitude and longitude lines meet, and it's not perfect 90 degrees everywhere, but it's also not as extreme. It's not as far off of 90 as we see on like the sinusoidal projection. So a compromise projection is if you're going for just an attractive final world map product, this is a good safe bet, right? And so you can see stuff like we've got some distortion up here, but still it looks pretty good. Okay, so the idea is, what I'm trying to stress here is that with these projections, you're not going to have perfection unless you're messing with a globe, right? But a globe is very limited in what it can do, what it's useful for. Maps are way more important. And so as long as you know what the projection is, as well as the coordinate system, the horizontal datum, all the stuff that we'll be playing around with the exercise portion of this stuff, once you know all of that, and you're consciously saying, yes, I'm going to have it projected here, I'm going to use this coordinate system, that distortion might not be a big deal, right? Because you know which projection you need for the task of the map itself, right? And another thing, too, is if you're working with kind of global maps, this is where it becomes important. But if you're working with something local, you're working for the city of LA or the state of California or whatever, we have some very specific coordinate systems and map projections that government agencies exclusively work in because it minimizes that distortion for, say, LA County, right? That distortion happens as you move further and further away, thousands of miles away, but it doesn't matter because we only want to map LA County or California or the Western US or whatever. So we'll see more of this. We'll play with more of this stuff, but this is definitely worth knowing, understanding what your map can do and what it can't do. Where is it accurate and where is it lying to us?